the final group of topics for this chapter is thinking about non-ideal systems, thinking about non-gas phase systems. So everything up to this point, we've assumed we're dealing with only gas phase reactions, which would be pretty limiting if that was the only thing we could handle. We're going to first cover non-ideal gas phase reactions. And the thing to remember here is that in our derivation of the equilibrium constant, we use this expression for chemical potential for a gas, that we have mu equals mu naught RT log P over P naught. Now, if we want to deal with non-ideal systems, we switch this for the non-ideal version of this equation, right? This is for the ideal gas. For a real gas, the simple thing that we do is we substitute fugacities, partial fugacities instead of partial pressures. And so our definition of Q, in terms of fugacities, we write this, say, as right with the subscript F to emphasize it's using fugacities, is that using our generic reaction that we started the chapter with, we would have the fugacity of Y raised to the stoichiometric coefficient of Y, fugacity of Z raised to the Z coefficient, fugacity of A raised to the A coefficient, fugacity of B raised to the B coefficient. That's the only thing that would change, and at equilibrium this would become Kf, where we replace all the pressures with fugacities. This is known as the thermodynamic equilibrium constant. And this allows you to calculate equilibria involving non-ideal systems. And so this is the whole point of defining fugacities in the way that we define them, is that we can still use the same framework of equilibrium constants, and all the non-ideality is built into these fugacities. And so these fugacities will then change as a function of pressure, as we have shown previously, and we can calculate them and tabulate them and use them in these equilibrium expressions. So this can be important in processes where we're at running things at very high pressures. So for example, one reaction that's terribly important in our world is the reaction to form ammonia from nitrogen and hydrogen. Left off, these are gas phase. So this process to form ammonia, which is used to make fertilizer, is a really important process. And this needs to be run at high pressures because you want to encourage the formation of the ammonia instead of the nitrogen and hydrogen. And so this, just to show sort of to show like the difference you get when you use fugacities versus, why did I close the PowerPoint? Sorry about that. I have some data here that shows the difference you get between Kp and Kf as a function of pressure. To emphasize the fact, all right, now let's zoom this a lot because it's kind of hard to see. Okay, so the blue dots that I have here are the equilibrium constant you would calculate as a function of pressure if you assume ideal gas behavior, so Kp. And then we can see at low pressures, these values agree with each other. So blue, but then blue becomes larger and larger. The equilibrium constant changes that you would get with pressure, whereas Kf, with using fugacities, stays about the same. And so we see there's a pretty drastic difference between if you don't take the non-ideal behavior into account here. So the fact that you're getting to these higher pressures and you have these intermolecular forces that matter becomes really relevant. And so this is an example of why you would need to use this non-ideal behavior. Okay, so, and then we can also write this in terms of fugacity coefficients, and you get your fugacity coefficient times your partial pressure. But yeah, this sort of sums up for gas phase behavior. In the next video, we'll look at reactions that include solutions, liquids, and solids, a lot of the reactions that we care about in chemistry, and what we do to take those into account.